welcome to the MSc Apex work tutorial series presented by Evotech CAE Ltd. This time we're looking at a wing structure case study and how the power of Apex can help us through the complete development process from concept to certification for a complex assembly. In this, the first tutorial of the wing structure case study, will explore some of the glued contact interaction techniques within Apex. We'll look at specific glued contact examples, highlighting highly idealized yet efficient assembly definition, primary sizing and load path assessment, and quick turnaround for trade studies and what-if analysis. Okay, so in this tutorial we're going to look at a very idealized structure made up for the sample wing box. So we've got wing skin, wing ribs and wing spars, as you can see with the skin removed. Very simple definition, and we're going to look at some trade studies with this definition to understand how the interaction technology using glue technology in Apex can help us quickly work our way around the model. So first of all, if we check the free edges on the model, nothing is connected, so there's no geometric connection between sub-assemblies, and you can see the red lines indicate free edges. So in this particular image, from the spar to the rib, there's no discrete connection whatsoever. Okay, so with the idealized geometry defined, so in this case just surfaces, we're going to define two-dimensional shell mesh, surface mesh, for the full structure using the default parameters for mesh type. With an element edge length of 35 mm, set the form taking the defaults. Meshing, meshes develop very quickly and easily. Element quality check, we can just have a quick look at. All entities are good, they're shown in green, and we have no poor, bad or invalid elements based on the default parameters. Element normal check, so showing the element normal consistency, and then the element normal vectors, so we can see consistency for the ribs and the skins. So the skin normal is important for air pressure loading, of course. Defining a material in the model, so we've got aluminium 7075 defined, assign that to the full model by a single sweep across the workspace. So all sub-assemblies are now defined with that material. Shell properties, or shell sections as Apex calls them. So we're taking out the wing skin from view and assigning a 5 mm thick shell definition with no offset to the ribs and spars. Taking those out of view and putting the wing skin back in, a 2.5 mm shell thickness with no offsets defined. Again, similar to material, very quick to define shell properties based on an auto procedure, which we're not actually doing here, but just doing a manual approach. But once defined, we can check with the 3D visualization to show how the shell properties have been defined. So very simple in this case. So 5 mm for the ribs and spars, 2.5 mm for the covers. So we take the wing skin out of view, so turn off the show for that, and shell thickness back on, and we can see that we've got our 5 mm thickness across the shell, rib and spar. So looking at the mesh definition, again, because we've got free edges, we don't have connectivity between the adjacent parts, either through physical connectors or geometry tie-ups. We can see that the mesh defined for the ribs and the spars is not congruent, and equally for the wing skin, when we bring that back in, it's not congruent with neither the rib or the spars, I should say. So you can see there's no connection whatsoever, and in fact no congruency between those adjacent sub-assemblies. So with the full mesh defined, quality checked, element normals checked, materials assigned, properties assigned, we now move into the phase where we tie the assembly together using glue technology. So this involves specifying a glue patch tolerance and a glue pair tolerance. So Apex can essentially define which areas of the model are connected within that tolerance, So it works on connecting sub-assemblies within the master assembly and also within parts for a given sub-assembly. So putting the glue patch display on, so we're now looking at every glue patch, glue pair within the model. So you can see at the sub-assembly level we've got spar to rib, rib to skin, skin to spar, etc, etc. So just showing the spars, so we've got part glue contact within that sub-assembly, discrete regions connected together. Putting the full assembly back on, and we can now see that we've got the connections at the sub-assembly level. Key thing to say in terms of the glue technology is, one, that it ties components together which don't need to have congruent mesh, so it uses an MPC equation or series of MPC equations to tie areas together so that you've got good force and moment transfer across the interface. And secondly, the shell moment transfer is defined as a function of those MPC equations, so you've got full moment connectivity across the glue contact. Okay, so once defined, we can specify loads and boundary conditions. So we've got a pressure load acting on the lower and upper surfaces, so we've got slightly higher pressure on the lower surface to give us the wing bending action, and then we're going to define and run the analysis. Analysis readiness can be used to double check that we've got the model defined and no pre-analysis errors are witnessed or experienced. So running the analysis very quickly for this fairly low resolution model, and we can see we've got wing skin displacements coupled with a wing bending action, which we can see if we turn off the wing skin displacements, which obviously mask the smaller wing bending displacements. So if we change the scale factor on wing bending, we can now see the wing bending action cycled through the displacement output. Okay, so pausing the displacement and then showing a number of different quantities that we can look at. So in this case we're looking at shell forces. So we've got the Fx, so the NXX to use standard Nastran terminology, running across the structure, so we can see the load that's being introduced in plane to the shells, which potentially causing an instability issue or similar, allowing us to understand and compare different models for our trade study. Okay, so moving on to the second approach, so we're looking at a different configuration. So effectively we've copied the original wing box to a different position in space using the transform tools, and you can see the original definition, so a copy of the original definition, 2 spars, 4 ribs. So what we're going to do now is reposition the ribs and reposition the spars to allow us to understand model response in terms of the comparison or trade study between the two different designs. So using the transform tools, we can simply move the left hand rib into the middle position and then delete the right hand rib to give us our new rib layout. Very straightforward with the transform tools. The generative nature of Apex means as we update or move an entity, the geometry, mesh and all the material and property definition downstream is maintained, so no need to redefine any of those parameters. So moving the rearmost spar, moving it in space, so taking a copy, and then moving the original back into the broad center of the rib. Now the problem with this is that of course we've moved the spar or the spars, and the parabolic shape on the rib means that the spars no longer fit the wing box, or they don't meet the wing skin as intended. So some very quick and simple tools using the geometry manipulation. So the vertex edge drag tool. So simply we're going to stretch the front spar way out of the wing skin or wing box so we can see the overall effect of that. Putting the wing skin back into view, we can see the change that we've made, and then it's a simple case of taking that vertex edge and dragging it back until we meet the wing skin as intended. So as we move it in space, the skin is highlighted in orange, and we know that we've snapped the edge back to that surface. Very quick and straightforward. And again, the generative nature means that we've moved the geometry and in turn moved the mesh the materials and properties. So much quicker approach than legacy methods. Okay, and now if we look, we can see that the spars are aligned with the what the skin would be, and equally with the ribs, so they're in the correct position. So just changing the view so we can see the model from a planar and an ISO view, just to show what we've done on the top skin. Repeat the process for the lower skin. Won't bore you with the mouse clicks, but the same approach. And again, going back into the glue technology and redefining those glue connections, because obviously we've now got ribs and spars in new positions, so we need new glue definitions. And again, using the default parameters, we can see the glue pair patches as defined, or defined within a given tolerance, so we can see the new spar in its position glued into the skin and glued into the rib, and equally the cruciform between the spar, rib and skin, we've got the glue pair defined appropriately. So if we expand the glue defined on the assembly level, so these are the glue patches between sub-assemblies, we can see those pair definitions and highlight them or modify them as necessary. And if we just show the spar defined on its own, we can see the glue patches at that level, as we see now. So we've got full load transfer force and moment across all interfaces based on the underlying MPC equations. But the glue technology allows us to manage those connections very easily. We don't need to get into any nodal definitions or any MPC creation types. So again, running the model for the second configuration as part of the trade study, and showing displacement and fringe plot of shell force equivalent to what we looked at in the first trade, the first assembly. We can now start to make some judgments in terms of how efficient our structure is, both in terms of rib and spar layout and cover response. If we had a requirement to hold a given aerodynamic surface profile, we could make decision as to what's the best structure. Okay, so showing the summary of our two concepts. So concept A, concept B, different rib and spar positions, and we've seen how the glued contact interaction gives us a very quick and easy means of modifying the structure, rerunning for a given load case, and making some broad decisions or analyses over the model response, and allowing us to move development forward very quickly without reams and reams of mesh edits, property edits, geometry edits to get to a given definition.
Okay, and thanks for watching. Please look out for further tutorials on this case study and other topics. Alternatively, you can visit Evotech CAE.com for specialist knowledge on MSc Apex and how it can be used to help with your FEA process.